Hello everyone and welcome. I am Manuel Antonio Cabas Montes, PhD student at the University of Barcelona, and today we'll do a presentation about a recent paper titled CO2 hydrogenation on Roux single atom catalyst encapsulating silicate, a DFT study and microgradient modeling study. Hope you enjoy. As you all know, global warming is one of the biggest problems of this century, especially due to the increase of anthropogenic CO2 expelled to the atmosphere. For this reason, finding ways to reduce or even better convert this CO2 into industrial interesting light fuels is a very studied topic. In our project, we study the CO2 conversion into carbon monoxide, methane, methanol, formaldehyde, and formic acid. However, those reactions do not happen spontaneously. For this reason, we need a catalyst. In particular, we will use single-atom catalysts. As the name suggests, they are only constituted by one atom and are used in hydrogenation, oxidation, and carbon-carbon coupling reactions. They present very positive catalytic properties, such as high activity and selectivity towards a certain reaction, and they are very economic. However, they also present a major drawback, because they tend to aggregate, forming nanoparticles if they are left alone, losing the positive properties. Hence, we need the support to prevent that. Now we will present our catalyst. We choose, among all the transition metals, ruthenium as our single atom catalyst. And as a support, we look into zeolite, which are porous structures very used to encapsulate single atom catalyst. In particular, we have chosen the silicate one in the group in the MFI, which is a pure silica zeolite. Here is an image of the encapsulated ruthenium in our silicate that constitutes our catalyst. Now that we've established our catalyst, we present the reaction pathway that we computed for the CO2 hydrogenation. In red, we can see the reactants CO2 gas and hydrogen gas, and in purple the different products in gas form that we presented before, and also water, which is also an important gas that will be expelled in our reactions. Our pathway is constituted of 47 interconnected elementary reactions. Using DFT calculations, we were able to compute reaction energies and energy barriers for every elementary reaction presented here. Next, we perform microkinetic modeling simulations to see which are the main gas products obtained at different temperatures at 1 bar of pressure. We can see that the main gas produced are water and carbon monoxide, followed by acid formic and formaldehyde. Also, we can see that increasing the temperature increases the production of the gases that we obtain. Next, we present the main reaction observed during the microkinetic modeling simulation, responsible for the CO production. From the DFT data, we expected that the main path for the CO production was the direct CO dissociation. However, we also saw that the carboxyl or COH pathway is also important, especially more important at 800 kelvins than in 600 kelvins, as you can see in the graphs. Finally, we would like to thank the founding institutions, the Ministerio de Ciencia y Innovación Universidad of Spain, the Maria de Maeztu program, the University of Barcelona, the IQTC Institute, and the group So, hope you enjoyed the presentation. The conclusion of this study are that we successfully convert the CO2 and hydrogen into carbon monoxide and water, as well as formaldehyde and formic acid. Now our main goal is to achieve the same simulations, but for a small cluster of ruthenium inside the silicate. In addition, we want to promote these two different studies, the one presented here and also the new one, at the multiscale. Thank you all for watching, and see you in the next video of Modeling the World.